So first of all, welcome everyone to this conversation with Agus Sudjianto. Agus, you have created probably the most well-known model risk management team. I think very active, very sophisticated, and it's great to have you here to talk about PiML and all your future plans, basically. So let's maybe start first with the beginning. You started your career at Ford as a product manager in the 90s. Did Ford do already model risk management back in these days?
This is an interesting question. So this is a little bit history, yeah. And I feel that I was born 25 or 30 years too early. The reason I say that was I did my PhD in machine learning, and my PhD dissertation was autoencoder, was neural network. That's when I got my PhD in mid-90, right? I got my PhD in mid-90. And at that time, when you graduated with machine learning, you do all of these things. No job as machine learning engineer, right? No job as data scientist at that time, whether you are a statistician or not, right? And I didn't have a statistics degree. All my statistics, probability knowledge is from signal processing, from pattern recognition and machine learning. So I am no way qualified to be a statistician. So when you graduated with that kind of degree, with that kind of specialty and no job, so what do you do? So I have been interning at Ford since my early graduate school days. So I have to do what I have to do. If you cannot be machine learning engineer, let's design real machine. So that's what I did. That's what we began working on engine and engine design. And when I left Ford in 2004, late 2003, I left after finished designing a brand new engine at that time, right? Yeah. And I was one of the engine design manager at Ford. We do a lot of when you design engine, you do a lot of model. We use a lot of sophisticated model, and you do design optimization with model. So it's no such thing as model validation, right? At Ford Motor Company, official MRM or anything like that. There's no such thing. The validation is real world, meaning you design it analytically, you design it with computer model, you build prototype. Here we go. Is your model working or not working? So that kind of things that we do, you design things, you do a lot of iteration with computer model, then you build prototype and you prove it, right? Because building prototype is expensive, and design through hardware is just impossible. To do iteration cost prohibitive, as well as too slow, because you have a very compressed product design. So computer model, mathematical model is becoming a necessity. But as an engineer, we say all models are wrong. This is directionally is good, is helpful, but we always take it with grain of salt. So that's what MRM basically is, right? If you look at MRM, we say, all models are wrong. We look at it with skepticism. All models are wrong, but these are useful. Now, when it's wrong, we need to know how wrong can it be, what is the impact of that, what is the harm of that, and what is the source of where the model can be wrong. And that's all, the whole thing. That's what all the endeavor in model validation is basically. Let's do it up front before we put model in production, so we know what is the weakness and what is the harm and the weakness, what are the risks, and know how to mitigate it.
Exactly. So indeed, but that means that because of all the costs back at Ford for building prototypes, because of the fact that it's very expensive, that there was already a lot of care actually done beforehand, right? Exactly. That's very interesting. Now, if we jump to today, or at least the recent past, then at Wells Fargo you built this great team, as we said. So it looks as if, say, the cutting edge techniques are introduced almost first in model risk management.
Mhm.
Is that a coincidence at Wells Fargo, or was this part of a definite strategy?
Yeah, it's from the beginning, from the strategy from the beginning. So when I came to Wells Fargo in 2013, I came back to US from UK, right? So before Wells Fargo, I was with Lloyds. So I came back and they want to the early day of SR 11.7 in the US, which is our guidance for model risk management. So the whole banking industry in the US going through transformation, creating what today is known as model risk management. So I'll come back to the US and thinking about, okay, yes, we have regulation, we have the expectation from regulator that we need to build. And that's the easy part, in my opinion, because yeah, this is a building block that we have to do. But then thinking about how can we make MRM not a compliance requirement or not a regulatory exercise, but really a strategy group for the company. How can we drive it? How can we make it like that? So it was by design at that time, a few things that done by design. The first is how are we going to do model validation? At that time, I put stick on the ground. To validate model, you have to build model. So you have to compare. You have to create model benchmark so that you can compare and assess the risk between the model that being proposed and model that you build you build yourself to compare. So that was the thinking, and then it's so every model validation, particularly for high tier model, it has to has model benchmark, model testing that built by model validation. To do that, then the model validation need to be 4 or 5 years ahead of model development because you can build the cutting edge. Now, with that, it necessitates to be everybody need to do some kind of R&D, research and development in model validation, which is very hard to do because you have timeline, you have compressed timeline that you have to do finishing model validation. So with that, then the thinking, okay, if that's the direction they want to do to really bring value, we need to have an R&D function that can work offline to build the cutting edge new methodology that model validator can use. So in very deliberate way, in Wells Fargo, the R&D, the research and development is in model risk management. So at that time, I hired somebody that I know very well, Professor Vijay Nair. He was the chair of statistics department of University of Michigan, and say, okay, why don't come join me? We know each other for a long time since my day at Ford, right? So join me and lead R&D function. And this is what we would like to do, an R&D function that will be looking at the most cutting edge, the most advancing the model validation techniques that model validator can use, and after that, model developer can use. So when model developer using the tool, it's all already tested very, very well and known by model validator. There are some advantages of that. The main advantage is become model validator becoming not a blocker. They are not afraid of new technique. They are not a blocker. They say, we know this thing. We are comfortable. We know the risk because we have used it. So that is very, very important. And then when the methodology later on adopted by model developer is already well tested and well known. So we did this from the early day of CCAR. So today is most of all the stress testing model that is in production, which is, by the way, very sophisticated semi-parametric model with coefficient varying regression and all of those things. It came from this kind of activity. So a model validator using it for quite some time in benchmark, and then later on get adopted by model developer. That's early day. And then when we come about in 2015, when we're thinking about, okay, we finished our regulatory stuff. 2016 is when when we pass at that time, we have horizontal exam across big bank, 12 banks, horizontal exam, and at that time we were the first bank who got satisfactory rating from regulator. We say, okay, we have the regulatory burden off our back. Now we need to focus on the future, and at that time, that's when machine learning stopped coming up too, and we looked at it. Okay, explainability will be big deal. We will be focused on this. So model validator working on the explainable machine learning, inherently interpretable machine learning, which today we put it in PiML and some of those things.
Exactly.
So it's very upfront like that. And then today, when our machine learning for credit decision model, using machine learning, we can use model that inherently interpretable. We know it, you know. So same thing in even very regulated model like stress testing. We are not afraid to use these things because we know how to use this. So it's very, very important and very deliberate in a way that the R&D and the advanced methodology coming from MRM.
Okay. Yeah, that's great to hear, and it's indeed a huge value if you can bring added value as a model risk management team. Exactly. Okay, so today we were going to talk about PiML. So let's you already mentioned it briefly when talking coincidentally about explainable machine learning. So what is PiML and what can we do with it?
Yeah, so PiML is really it has two components, and I'll talk about the history and why we put it there. In model validation, according to SR 11.7, it has three main components. One is what we call conceptual soundness. Two is something that the SR 11.7 called outcome analysis. And then the third pillar is really ongoing monitoring. Basically, do 1 and 2 all the time, regularly, right? So the main topic is really two components: conceptual soundness and outcome analysis. Now we'll talk about that in more detail what they are. So I'll probably do the second piece first on the outcome analysis. And this is really dealing with machine learning. This is the interesting piece of model validation, and why we put PiML. We'll talk about that. Model validation is an interesting, if you step back, you know, I've been in this area for a long time. You step back and thinking, what do we do in model validation? What is really we do in model validation? Well, there are a few components that are critical. One is understanding key model risks. For the purpose of the business, here is the intended use of the model. And what can go wrong, that's really key model risk. And where the root cause of what can go wrong, and etc. And we need to be able to measure it. So we have tolerance. We measure, okay, here now we're going to measure the key model risk. Yeah, measurement, here measure it. And we're going to test the model according to that. Now, this is interesting because in traditional model, where the way people validate is a lot of statistical exercise. And the statistical exercise mainly are hypothesis testing, meaning that in statistical model, somehow we have imaginary things that there are a stochastic process of generating data. There are a probabilistic stochastic process of data generated. And then all the testing and tests, doing hypothesis testing, whether that are fulfilled. So doing hypothesis testing. But to me, and a lot of people are angry at me here saying this, but to me, you're doing hypothesis testing, nothing to do with model risk.
Exactly.
So you test model, you validate model, but you don't manage the risk, because you're really testing your hypothesis. Now, this is interesting in machine learning. In machine learning, there's no such thing of assumption of data generating function. So no hypothesis testing anymore. What kind of hypothesis testing? No such thing, because it's no generating function. So all the statistical testing that people traditionally do in that is no longer there, because then which I feel like is the right way to do, because in real world, no such thing is really ideal generating function. At the end of the day, model will work or don't work. And how do we detect model will not work? That's not hypothesis testing. So PiML coming from that. And also the other thing is people in machine learning, people measuring the mean, the average, people measuring AUC, people measuring MSE, mean square error. Those are average measurement. My experience in product design, back to the 4 days, product will not fail in the average. Product will fail at the tail. Under extreme condition, in certain condition, product will fail. So we need to think about that mindset too. We cannot just validate and measure based on average, based on AUC, based on MSC, but really identifying which region, which condition that the model will be wrong, and why is that. So that's really the key thinking, that we would like to do that and speak about this. But how to make it real? So we have to create put the software. This is how we do it. This is to enable other people to learn. So if you look at PiML, I'm talking about 2 components: conceptual soundness and outcome analysis. What is in the conceptual soundness? Conceptual soundness, it has, at least in my mind, 4 components. One is the data quality and suitability. Is your data good and representative, and this is the data that we can trust to build model? So in PiML has all of those, and several things that very basic blocking and tackling that many people do, how people treat a missing value, how you do the imputation, how you check the outlier, and all those things. So data quality, suitability, which we can talk about Gen AI later, which this get violated deeply. Second principle in conceptual soundness is input control. Now, you have to control the input. What does that mean in model development and model validation? Well, we limit the model, we choose the variable selection, right? So we choose the variable selection, and we also control the range, at what range of value of each variable. So it has the variable selection. The third component is explainability and interpretability, which is very foundational, looking in the relationship between input and output and be able to explain it. So that's and understanding the relationship between input and output makes sense. So that's very foundational. And then the 4th component, benchmarking with models that are conceptually sound. And in machine learning, this is very important, because a lot of machine learning is a black box. So we put a lot of model benchmark that are inherently interpretable. So in PiML, that's why a very unique feature in PiML, because of this 4th component, benchmark it with model that conceptually sound, that I know exactly the model behavior. With that, we put the sophisticated machine learning that are inherently interpretable by controlling the architecture. If we use boosting machine, we can boost it up to 2-way interaction. Then we can see the main effect and the interaction. So in PiML has XGB1, which is basically a main effect model, XGB2, which is main effect with interaction using gradient boosting machine, and then use Caminette. If people want to do neural network, you can do it the same way with neural networks in Caminette. So those are the really main 4 component and on conceptual soundness that we put in PiML. And then when we talk about outcome analysis, so the first critical thing in outcome analysis are really the model weakness. Which area, which variable, in what range, combination of variable, in what range. that model performance is weaker, where the AUC is below the average, where the MSE is above the average, right? So those identifying weak region. So that's one very, very important, because that's where model more failure will be identification of weakness region. Second is because model have uncertainty, outcome uncertainty. Outcome uncertainty is fact of life. What's important is understanding which condition, which region that the uncertainty is bigger. So that's what we want to find. Okay, yes, we live with uncertainty, which region that the uncertainty is bigger, so we know how to manage it, whether to improve the model or during model usage. Make sure you watch for that, because you have higher uncertainty. If you're doing credit underwriting, you're thinking, well, this is have high uncertainty in this. Do you really want to do it? You want to approve this region because it has high uncertainty. The value may be, yes, you may approve it just looking at the mean, but the uncertainty is big. And the uncertainty typically show up during bad time, right? During credit term. So understanding uncertainty and the region where the uncertainty is very important. So that's, we call it reliability. That's in PiML. The third component is really uniquely machine learning, I would say. It's about model robustness. Because machine learning, especially gradient boosting machine, it can be very flexible, a lot of capturing the data so well, and even you still have good generalization. So make sure that the model is robust against small perturbation. If you have small perturbation, small noise, additional noise on the input, your model performance, your model will not react dramatically. And a lot of machine learning is problematic because this one typically undetected, in the sense that we have what we call it in machine learning is in overly parameterized model is what we call it is benign overfitting, because we split data into two randomly. So the two, testing and training, stochastically, they have the same distribution. So when you overfit, you will not detect it with the your testing data unless you inject noise on the testing data, then suddenly it show up. So that's what we put in PiML as well. Make sure that you design model that is robust, not only looking at the mean performance, but looking at robustness, because model that winning in the AutoML, it can be model that really bad because not robust at all. You put in production. So that has to be tested. And then the fourth component that's very important is understanding the effect of drift. When the input drift, how the performance going to materialize in the performance, and understanding what variable, because not all variables are important to be watched. So under data drift, and really assessing the performance under drift, and identifying which variable, key variable that you need to monitor. That's what we put in PiML. So 4 principle in conceptual soundness, 4 principle in outcome analysis, and then we put the 9, the very number 9 that's important is model fairness testing. So that's what we do in PiML. We try to inject the thinking of model risk, that it's no, and if you notice here, no hypothesis testing.
Yes, exactly. But a lot of tools to understand and to inspect a model like a real engineer, I would say.
Yes,
so I really like this. Unfortunately, time flies and there is a limited number of additional questions we can ask, but maybe one question that springs to mind a lot when talking about all these high dimensional models. You talked about region of validity, about measuring the uncertainty. So since typically the amount of input variables is extremely big, ultimately, like representing a region of validity, for instance, is a fairly high dimensional exercise. So how do you deal with that in PiML?
I think a few things that you can do in that, right? One is, this is why identifying factors that are important. Driving factor that important on the robustness, factor that important on reliability, and all of those. so that you can focus on very few variables that really important.
Or combinations of variables, probably.
Combination that important. So that's the thing. But the other piece that you can do as well is the our traditional statistical techniques, dimensional reduction, right? So you do dimensional reduction so that you can visualize it. And this is, by the way, is important, more important in language model. Because language model, the embedding dimension can be very, very high. Yes. So how do we do the embedding dimension on this? So stay tuned, watch for this, because tools are coming probably in the late May or early June. So we're still building this tool to do it for PiML style for language model, dealing with high dimensionality, how we're going to look at interpretability, because now we're dealing with high dimensionality and language has no cardinality, no ordering. So how do we do it so that we can see it, we can group them? So that's really becoming more important in language model.
Okay. And is that also like your main plan with PiML to bring this high dimensionality into it and to help to also extend the capabilities towards generative AI models and language models? Yeah.
Yes. So that's we going to have a PiML style of language model in late May, early June. Still working on it.
It's going to be a very big pie, I'm sure. So thanks a lot, Agus, for this very interesting conversation, and thanks everyone for joining. It was really interesting, and we're looking forward to all the upcoming versions of PiML.
Yes.
Thank you.
Yes. Thank you. Thanks for the support, and give a GitHub star to the developer. Show your love to the developer. All right. Thank you.
We will. Thank you.